Swayam Prabha. Digital India. Educated India.
Today we are going to be talking about computerized layout planning. If you recall, last time we had talked about the layout planning problem in general and had seen how process layouts could be designed. In this particular lecture we are going to look at some computerized packages which are available for solving this problem of layout planning, and we will see how exactly they help us in developing a layout. Broadly speaking, layout planning packages that are available could be classified into two broad categories. We could talk of what are called construction programs, and we could talk of what are called improvement programs. Construction programs are those programs which try to generate the layout plan from a scratch. That is, you don't need any initial layout as an input. By utilizing the information that is available about the layout, you can generate a layout from a scratch. And the important programs in this category are CoreLab, ALDEP, Planet, LSP, Layopt, RMA, Comp1. These are all commercial names, and we will look at one particular type of construction program in detail, that is ALDEP, which was one of the early programs that came on the scene, and it summarizes the mechanism by which the layout plans can be generated. On the other hand, when we talk about improvement programs, we require an initial layout of the system as an input. What really these packages do is they tend to improve upon the layout, and some of the packages that are popularly used are Craft and RUGR. This particular package is based on graph theory. So we'll try to look at one of these packages, the more popular one, namely Craft, in some detail in today's lecture, so that you get a flavor of one of each of the programs in the category of construction and improvement programs. Let's look at ALDEP. ALDEP, incidentally, stands for Automated Layout Design Program, and it was developed within the IBM, and this is the original reference of the particular package. It was a paper by Seehoff and Evans, the two people working with IBM who developed this program, and the title of the paper is Automated Layout Design Program, the Journal of Industrial Engineering, volume 18, number 12, 1967, pages 690 to 695. The basic idea behind ALDEP was that LDAP is based on the activity relationship chart. If you recall the discussion that we had in the last lecture about systematic layout planning and the procedure for systematic layout planning, we saw that there, after computing the material handling relationships, you assign certain activity relationships between all pairs of departments, and these activity relationships were called A for absolutely essential, E for essential, I for important, O for ordinary closeness is okay, U for unimportant, and X undesirable. So LDAP is based on this scheme, and this very scheme is subsequently used for purposes of scoring different kinds of layouts. These are the values, numerical values given to these numbers. So it is 4 to the power 1, 4 to the power 2, 4 to the power 3. So this should be 4 to the power 2 here, and 4 to the power 3. And the X, which is a highly undesirable requirement between two departments, is given a negative score of -4 raised to the power 5 in that sense. So these are the numerical ratings that come. So essentially this is rated on a logarithmic scale in that sense of the term. LDAP has a capability of handling 63 departments on 3 floors when the package is operated. Let's see the scoring pattern of LDAP. What is being done when you are scoring a particular layout? For purposes of scoring the layout, you sort of divide the entire area into equal sized squares. And what would happen is that if you are looking at one particular square, let's say we are focusing on cell 0, each cell will have 8 neighbors, which are shown here, right? So for cell 0, the scores of all the 8 neighbors are added together as per the REL chart, which means if cell 0 belongs to a certain department and this belongs to the same department, then no contribution to the score. But if this particular thing belongs to another department which has an A rating with this, then depending upon the value for the A rating, you will have that much of score coming out of this interaction. Then similarly for 5 and 0, similarly for 0 and 6, and all these values 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, that means all the neighbors of this particular cell would be evaluated and would be given marks. And then after having done that, cell 0 is deleted so that it is not counted again. So you can put a cross on cell 0 and go to the evaluation of the next cell in the whole scheme of things, and I evaluate all the neighbors for that particular cell and keep on adding the values there. So we then proceed to the next cell till all cells are exhausted in the entire space, and the final cumulative score is the layout score. So this is the basic procedure by which LDAP assigns a score to a layout. I would like to mention here that LDAP is based on a lot of random features, and the basic advantage of having these random features is that if you run the program a second time, you will probably get a different layout and a different score. So if you run the program a number of times, each time you will get a different layout with a different score because of the randomness which is built into the program. So obviously if you run it, let's say 100 times, you can always select a layout which is the highest score. So that is basically the idea in using LDAP. So here are the input requirements for LDAP. What is the input needed? You need the length, width and area requirement for each floor on which you are going to do the layout. As I indicated to you, LDAP has a provision for handling layout problems on 3 floors. So you have to specify this information. You need to specify the scale of layout printout, which is generally maximum of 30 by 50. You have to specify the number of departments in the layout. You have to talk about the number of layouts to be generated. I indicated to you that the number of layouts to be generated is a large number of layouts can be generated, and each time you generate a layout, you can get a different layout and you can get a different score. So the purpose of this particular exercise is to try to get a layout with the highest score. So, but in order to cut down on computer time, you specify a priori what is the number of layouts that you would like the program to generate, whether you want 20 layouts, 50 layouts, and so on. Then a minimum allowable score for an acceptable layout can also be fed in. In the beginning, when you run the program for the first time, you have no idea what it is. So the program generally runs that you first time you generate 10 layouts, say, and maybe the highest score is 120. So in the second time that when you run the program, you can specify the minimum allowable score for the layout as 120 and run the program again. And maybe on the second run you generate 20 layouts and the highest score that you generate is maybe 250. And the third time you specify the minimum allowable score as 250, and suppose you don't get any layout, that means the best layout is the one with a score of 250 that you had generated earlier. So that can be the typical stopping criterion for LDEP. The minimum department preference can be either A or E generally. What this means is that if a department is already placed in the layout, the next department which you pick up for placing adjacent to that department should have a high activity relationship with that particular layout. So it can be specified as A or E. You need the REL chart for the departments. You need the location and size of any restricted area for each floor. So these are essentially the requirements for running LDEP in that sense. One other feature of LDEP is how it places the departments in the layout. What it does is that suppose this is the area in which you want to develop the layout. What it essentially assumes is, it assumes that there is a constant width, and suppose you want to locate a department, you will have it's like saying that this is the width of a sellotape, let us say, and you keep on unrolling the sellotape in this direction, and you know the area of the department, so you can find out what length of the tape you need to represent the area. So you can represent the area in one way, and then once you come to the end, you can start representing, you can start putting the tape in this direction and in this direction and in this direction till you follow this scheme. So this will give you a manner by which you generate the layouts. This pattern is known as the vertical scanning pattern, because we are vertically scanning the area and taking a strip of the required size and putting it there, and then the next department comes from here and we put it there, and then the third department, and then the fourth department, and so on. So this is the mechanism that is adopted in LDEP for placing the departments on the shop floor. Here is a brief glimpse of the mechanism of LDEP, that is the algorithm that is followed by LDEP. The first step is the first department is placed randomly. After having placed the first department, the second step is to scan the REL chart which you have for a department with an A or an E rating, that is the minimum department preference whatever you specified, and continue this step until no such department exists. So what happens really is that you place the first department at random, and then you have to pick up another department which has a closeness rating, That means when you are trying to locate friends in a hostel, you locate the first person randomly, and then you pick up a second person who is very friendly with the first person and place him next, and then again put the next person which is very friendly, and the friendliness here is being determined by the ratings A or E on an REL chart. And once you find that no such department exists with an A rating or an E rating in the REL chart, then pick up the next department in a random fashion. Just again take the example of locating friends in a hostel. Once the friends have been located, we don't find a friend, we pick up any random person and put him next, and put him next, and keep on doing this exercise. So pick up the next department in a random fashion and again proceed by scanning the REL chart, which is the step B. So we can continue with this exercise till we develop a layout. Now let's see, try to get an idea of what the whole thing will look like if you follow this procedure of LDAP. We start with the available space. We want to locate, let us say there are 4 departments, let's call them A, B, C and D, and we want to locate them in this particular space. So what's going to happen is we are going to be constrained by this width. We are imagining that each department is cut out on a strip of constant width, and we will cut out the length depending upon the area of the department which we know, and we will allocate that in this. So from this we pick up a department at random. Picking up a department at random can be done very easily by using random number tables or generating random number tables in the computer. Suppose the random department which we pick up is department B. So we place department B here, and this length is such that this satisfies the area requirement for department B. Okay. After having placed the first department using this vertical scanning pattern, we are now looking for placing departments next to it. So what we do is we look for in the REL chart for a department which has an A rating or an E rating with department B, and suppose we find such a department. So what we do is, suppose that department is D. So what we do is we place D like this, but then the space is over. So then LDAP says that you place the department D and you cut the strip like this and finish it off here till you have accommodated the entire area for D. So now at this stage we have placed 2 departments B and D on this particular thing, and we are now looking forward to placing the third department. As far as the third department is concerned, what we would do is we would again scan the REL chart and try to find if there is a department which is friendly with D, depending upon the minimum department preference. So based on that information, suppose that in this particular situation department A is a department which is picked up for placement. So we place department A depending upon its requirements here. So we have now been able to place 3 departments in the layout, and then the next department, which is in fact we are talking here about the 4th department. That means there are only 4 departments, so only 1 department is left. So that particular department has to be the one which is to be placed next, that is department.
If A has some X kind of rating with B, then because it is close to
It's
B,
not taken into consideration in LDAP. In LDAP what is being considered is only that A has a friendly rating only with D, which you are placing next to it. It can happen that in the process of placement A and B might not get along well, but that's not taken care of in LDAP. Okay, so that's a limitation or a drawback of LDAP. You are very right that if you keep on following this vertical scanning pattern, it may so happen that you have placed department A next to D, but the neighbor on the sides might not get along well or might have a low rating with this. But the beauty of LDEP lies in its simplicity, and there is no idea or there is no attempt in this particular procedure to gain an optimal solution in that sense. And moreover, since the program can be run again and again with different random numbers, that's what it is. So you are likely to get different layouts, and each one can be scored, and you can then determine this. But this would remain a major limitation of LDEP.
Then if there are two departments with rating A, then with B, then?
If there are two departments with A rating, you take one at random in this case, any one at random. Now finally, we talk about the fourth department. The fourth department is C. So C is placed here, and suppose it's a big department, it goes on like this, and then it goes on like this, and it finishes here. So you will find that the shape of the department is something like this, as far as C is concerned, as a consequence of the vertical scanning pattern. Now this is, in fact, this would become, if there were only 4 departments to be located, our final layout, right? So let's see the final layout, and let's try to make some comments on the final layout that you get in LDEP. You now have a fair idea of how it operates. It has elements of randomness built into it, so that the starting department could be different, and depending upon the starting department, other departments could keep on change in subsequent runs of the program. You notice that departments need not necessarily have rectangular shapes in this. For instance, look at department B. D. It has a very peculiar shape, and no company would probably like to have a department which would have this kind of a shape, or it may, I don't know. Similarly, look at department C. C has a very peculiar shape. It's a jutting position here, and then this whole thing, and then you have something like this. So you have C has a funny shape. So one of the features or one of the drawbacks of this particular procedure is that you land up with departments, and some of the departments may be non-rectangular. Of course, some are rectangular. B is rectangular, A is rectangular, but some of the departments could be rectangular. And another thing which happens is that the final boundary need not necessarily be rectangular. It could be rectangular. It could be rectangular if the total area of the departments is equal to the total space that you have available. So if you make a provision that you want to locate the departments in exactly a certain space, and you make sure the total area is the same, and that area you divide into strips, then of course this would happen. But if you just lay out something in the area, then the final boundary that you get is also very peculiar, right? And therefore this would give you some insight into how LDEP actually operates in terms of generating the layouts, and it uses a very simple principle of that scotch tape or the edge tape. You keep cutting the departments according to the size and pasting them there, and you keep on and it's basically the simulation of that LDEP really tries to do.
So this problem of funny shapes can be taken care of if we can iterate with different widths of the strips, if we are able to iterate with different widths.
Yes, it can be taken care of to some extent if you take different widths, but there is no guarantee. It's a hit and trial procedure. You don't know exactly what would be the size, right? Because what can happen is a department might finish here, and the second one might have to end up somewhere else. So there is no guarantee that this would happen when you follow.
What happens if the department C has X rating with all the other 3 departments? Will it be placed very far away?
No, what would happen is that all departments which have an X rating are generally placed randomly in this case. So they could be coming anywhere. But in this particular case, the placement of C is governed by its relationship with A, which is where you cut off the tape last and then place it. So obviously you would always have situations where certain departments could be negatively placed with regard to other departments, and this is essentially a serious limitation. But I think the purpose of this exercise of LDEP, which was one of the early programs that came on the scene, shows that by using simple logic and by using the concept of randomness, you can generate different types of layouts. And because of this randomness, you could run this program a number of times, get alternative layouts, and then you could pick up the one with the highest score. That was the basic idea. So the idea was never to find out an optimal solution. It was trying to find out the best from amongst the ones that you generate. Another feature, another program that we talk about, which is a construction program, is CoreLab, which incidentally stands for Computerized Relationship Planning. Now, computerized, you see, what happened was that one of the major drawbacks with LDEP was non-rectangular shapes. So in LDEP, what was done was that each department's shape was fixed first. That we want department A to be rectangular, department B to be rectangular, and so on. So you fix up the shapes like that. And then what was done was, you pick up a department at random, not at random, it's based on what is called the total closeness rating, the total placement ratio or the current placement ratio, which means essentially that the department is placed centrally first, and then around that you build other departments. So I place a block in the middle, and then I take another block. Which one do I take? Depending upon the relationship diagram and some calculations based on that. Then you take that block, and I can place it anywhere along the boundary. So I find out in placing it along the boundary where I should place it, and that particular point, whichever is the best, you place it there. Then you have a block of two departments, one department and the next department. Then it has its own boundary. Then you pick up a third department and place it along that boundary of the two departments, and you place it somewhere, wherever according to the placement you are getting the best value of the objective function, and so on. You continue this. So this was basically, and this was the attempt in CoreLab to experiment with rectangular shapes, and the layout is built around a central department, and the placement and the choice ratio is based on the total and current placement ratio. We will not go into that, because you can always devise other objectives or other criteria and metrics to choose that particular department, and the final layout on this case also may end up with irregular boundaries, because even if you have different departments, you start with a rectangular department, you place another one, you place another one, ultimately there is no guarantee that the boundary of the whole thing will be rectangular. So at least you have rectangular departments, but irregular boundaries could result. So this is the basic feature of CoreLab, which is another program for, it's also a construction program which generates a layout from a scratch. Let us now talk about the other category of programs which are used, and we will talk about CRAFT. CRAFT is a procedure. CRAFT stands for Computerized Relative Allocation of Facilities Technique. Computerized Relative Allocation of Facilities Technique. CRAFT was actually a procedure that was developed by Volman Buffa and his students. You've heard of Buffa? Buffa was a professor at the University of California at Los Angeles, and he's written that book, Buffa Modern Production Management. Right? Must have heard of that book. And these are the original references for this particular. So it was basically, he involved Armour and Buffa, a heuristic algorithm and simulation approach to relative location of facilities. This was the first paper which appeared in Management Science, volume 9, number 1, 1963, pages 294 to 309. And a second paper based on this was by Armour and Volman. So it's like saying that Armour was the first person who did his BTech with him, and Volman in the next batch did that project with him, and he had this paper called Allocating Facilities with Craft, published in the Harvard Business Review, volume 42, number 2, 1964, in pages 136 to 159. These two papers actually give the details of this particular procedure called craft. Now we look at this procedure. This particular procedure, before we take an example of craft, is actually an improvement type algorithm. So an improvement type algorithm means that you have to specify an initial layout for the departments, and all that you do is you try to fiddle around with that layout and try to find out if a better layout exists. And the objective function that has been chosen in craft is minimization of the material handling effort. You would recall that quite often in the design of process layouts, the material handling effort is a major problem, and the intention in designing these layouts is actually to minimize the total material handling effort involved. So this is an explicit attempt by the originators of craft to look at the material handling effort and trying to reduce it in developing a layout. Let's look at the major inputs required for this particular package. If you recall the systematic layout planning procedure, which says what are the various inputs like. These inputs are pertaining to the product, process and schedule, right? So let's take an example, and in this example what we find is that we are dealing with three products. Let's call them 1, 2 and 3. Suppose a company is interested in making these three products, and let us suppose that the processing sequence, that is the process information for these products, is that it has to first start in department A, then go to B, then go to C, then go to B again, then go to C, and then finally come out in department D. So the processing sequence is fixed by the nature of operations required of product 1, and let's say the daily production is 100 units. And now in all, these are all products which could be of different sizes, right? I mean that's what we are trying to say. But in terms of material handling effort, we would like to combine this information in the form of a common material handling unit. So you can talk in terms of trolley loads per day, because the material will be moving in the factory in, let us say, trolleys. So what we are trying to say here is that the number of items this can be accommodated in this trolley for product 1 is only 5. Similarly 5 for product 2. What it means is that product 1 and product 2 are roughly of the same size, right? And as far as this product is concerned, this is much smaller in size. So 40 products of this size can be accommodated in the same trolley, and our unit is movement in trolley loads. So this is what it is. So if this is the daily production, we can determine the number of trolley loads that we will see moving of these products in the factory. So 100 by 5 is 20 trolley loads per day will be moving of product 1, and 50 by 5, that is 10 trolley loads will be moving of product 2, and 40 by 5 200 by 40, that is 5 trolley loads, only 5 trolley loads will be able to carry these items, because these are relatively small items, huh? So these could be like very small items, these are relatively bigger items. So you need only 5 trolley load, nuts and bolts that you need, something like that, which can be carried in only 5 trolley loads per day. So the information that you need, this is the input information that we are making 3 products. This is the sequence of operations of these products, and each of these products will require a total movement of 20 trolley loads, 10 trolley loads and 5 trolley loads per day in the plant. So we know the total quantum of movement in the plant. The second thing that we need to specify as an input is the initial layout for the plant. For the sake of simplicity, we are assuming that the 4 departments A, B, C and D are initially laid out in equal squares as shown here. Okay. So this is the initial layout. A is here, B is here, C is here and D is here. So the 4 departments are located here in equal squares. And for this particular layout, you can easily determine the distances between the various pairs of departments. For instance, if I go from A to B, I have to travel a distance unit of 1. We are measuring distances between the centroids of the departments, and we are assuming, for instance, that the side of each of these squares is 1 unit. So A to B is 1 unit. A to C is 2 units, because I am assuming that you will have to go like this from A to C. So 2 units. From A to D is 1 unit. Similarly, B to A is the same as A to B. It need not be, because travel may not be, I mean, here we are permitting two-way travel. So B to A is 1, B to C is 1, and B to D is again 2 units. And similarly here. So this matrix, this 4 by 4 matrix, is actually nothing but the distance matrix corresponding to this layout. If I change the layout, obviously the distance matrix will change. Okay. So this is the distance matrix for the initial layout, which is what we are assuming here, A, B, C, D placed here, and we are assuming that rectilinear distances are involved. That means I am going from here to here, not this way, not this way. So I am talking about movement using rectilinear distances. So this is the information pertaining to the initial layout. What we can then do is determine a matrix known as the load matrix for this particular information, which is the total quantum of trolleys which are moving between all pairs of departments. How do I compute this information? This is the load matrix. What is the load moving between all pairs of departments? Take, for instance, this particular value, which is from A to B. So what happens is, look at the product, process and schedule data. What you find is the only movement from A to B is this one. A to B is here. There is no other A to B movement here. So A to B, the total movement is 20 trolley loads per day. So I enter this 20 trolley loads per day. Similarly, I look at A to C. What happens in A to C? Look at this diagram again. A to C does not occur in the processing sequence of product 1, but you have A to C here and A to C here. So the total movement from A to C is going to be 15 units. So I put 15 units as the movement that takes place from A to C. There is no movement from A to D, but you have, for instance, movement from B to C. Look at the movement from B to C. There is a movement from B to C here, and there is another movement from B to C here, and there is another movement from B to C here. So it's going to be 20 plus 20, 40, 40 plus 5 is 45. 45 trolley loads are going to be moving from B to C. That's what you're going to see in the plant. Okay, and from B to D, let's look at B to D. There's no movement from B to D here. There is B to D here, and there is B to D here. The total movement is 15 trolley loads. So this is 15. The total movement from C to B, similarly, it's you can see from C to B you have a movement here, and from C to B you have a movement here, and from C to B you have a movement here and a movement here. C to B is 10 from here. 10 plus 10 is 20 here, 20 and 20, which is 40 here. So that talks about the movement from C to B. Yeah, there is another 5 here because C to B occurs 2 times, right? So it's 45, and the movement from C to D is 20. So the idea is how to construct a load matrix. A load matrix is actually summarizing the total movement that takes place between all pairs of departments, and you know the number of trolley loads moving. For instance, you find that the maximum movement takes place between B to C and C to B. Does this give you a hint? The hint is obvious, that these two departments should be close to each other if you want to minimize the material handling effort. That's what it is, right? So we construct this load matrix. The next thing we do is that we might have a unit cost matrix. A unit cost is nothing but the cost incurred in transporting between different pairs of departments. You could be using different methods of material handling between departments, okay? So between A to B it could be manual, between A to C it could be some kind of a motorized trolley or something of that kind. So the cost might be double of that, right? So and so on. Similarly, say B to A is manual, B to C is manual, and so on, but C to A could again be a motorized trolley or something whose cost is double. So you have a matrix which we call the unit cost matrix. This is an input to the problem, okay? We are still trying to identify the major inputs to the problem. If you have, for instance, all movements taking place by the same material handling equipment, then this matrix will be all ones, and you can in fact forget about this matrix, right? So what we do is we construct a matrix by multiplying the load with the unit cost matrix, multiplying element to element. So what will happen is, this was 2015, so we have because the cost here was 2, this becomes 30. So 20, 30, 45, 15, 45, 20 is what we call the flow matrix. The flow matrix is determined by multiplying the loads moving with the unit cost. So we have this, and this is the flow. So you can say, if you take the summation of each row, what do you get? From A, totally 50 units are moving. From B, total of 60 units are moving. From C, total 65 units are moving. There are no units moving from D. And similarly, to A, nothing is coming. To B, 65 units are coming. To C, 75 units are coming. And to D, 35 units are coming. If you have a vacant row or a vacant column, what does it show? If I have a vacant column like A, it shows that A is a source. If I have a vacant row, it shows that this is a sink. So basically in this problem, A is your raw material store and D is your finished goods store. Everything starts from A, so there is a movement from A and there is a movement to, that's it. And as far as D is concerned, everything settles down in D for further transportation to customers. So this matrix is called the flow matrix. Incidentally, for this problem we have to construct the flow matrix only once, right? We have to construct the flow matrix because it summarizes information pertaining to how much flow is taking place between all pairs of departments, and we have a 4x4 matrix which summarizes this information. Now for the initial layout, what did we have for the initial layout? We said that our initial layout is the 4 departments are placed A, B, C and D like this. So this was the distance matrix for that particular layout, right? For instance, between A to C there is a distance of 2, otherwise similarly B to D is a distance of 2, C to A is a distance of 2, all other distances, and D to B is also a distance of 2, all others are 1. Now we utilize this information pertaining to the distance matrix and we compute what is called the material handling effort for the initial layout. So the initial layout, this is the flow matrix, this matrix that you're seeing, which we have computed. This is the distance matrix for this. So we multiply the flow matrix with the distance matrix, we get the material handling effort. For instance, we get the material handling effort here, 20 into 1 is 20, 30 into 2 is 60, and similarly 45 into 1 is 45, and 15 into 2 is 30, and so on. So you get this particular matrix here, which is the material handling effort, which is what you are interested in compiling ultimately. And then you can sum the rows and the columns if you so desire. Actually, you need to sum only one of them to get the material handling score. So this is 20 plus 60 is 80, 75, 110, 0. Take the sum of this column, it's 265. What is this 265? This is like load into distance. It's like saying I move 5 trolleys and for a distance of, let us say, 100 meters, right? So load into distance is giving me the total material handling effort. So this is my objective function. This is the crucial value that I am interested in this particular case. So this value is arrived at, let us recapitulate. It's arrived at by taking the flow matrix, multiplying it with the distance matrix for the layout. The distance matrix is the one which is dependent upon the layout, isn't it? And by multiplying these two, you ultimately get this figure, and this figure summarizes the total material that, for instance, between A to B, the cost of material handling is 20 units, rupees. A to C, it is 60 units. So total material handling moved from A to all departments is 80. So 80 rupees worth of cost is incurred in transportation for all the trolleys that leave from A. Similarly, all the trolleys that leave from B, 75 units of money is the cost, and so on for C and D. And the column totals will tell you the amount of, for instance, 110 units of money is the total amount of trolley that land at B. From where does it land from? It comes from A and C. So it tells you exactly that from A and C there are going to be dispatches every day of 20 and 90 units in terms of money to this particular thing, and the total material handling cost therefore is 265. So in essence, what we have done till now is evaluated the cost of the initial layout. We have an initial layout which is an input to the package. We have determined the load, and the multiplication of the load and the unit cost has given us the flow matrix. The flow matrix and the distance matrix has given me the material handling effort, and it can be used for this determination here. So here we have seen how the material handling effort for the initial layout can be calculated. Now our basic intention is to use this information for improving upon the layout. So the improvement in the layout is possible in the case of craft by interchanging departments. So we have 4 departments, A, B, C and D. If we talk about pairwise exchanges between these departments, the number of possibilities is going to be 4C2. So you will have 6 possibilities. What are these possibilities? You can interchange A and B, A and C, A and D, B and C, B and D, and C and D. So what happens is, for instance, that if we interchange A and B, what will happen is that this particular initial layout will be modified to B, D, A, C. Similarly, with if we interchange A and C, what's going to happen is that the layout A would come here and C would come here and D and B. So this would be the new layout that we could generate from here. So similarly, these are the 6 new layouts which could be generated by pairwise exchange of different departments, and we have got these all these layouts. You see, the intention now is that for each of these new possible layouts which are derived from the initial layout, you can develop a distance matrix. Only thing that will change is the distance matrix, and the flow matrix will remain the same, the total loads which are moving. Multiply the flow matrix, so flow matrix with the distance matrix, and compute the material handling effort for each of these. Let's see, for instance, how this can be done. For alternative 1, which was this, that means if we change the layout to BDAC, what it means is simply that the distance matrix will now look like this. The distance matrix has changed because distance from A to B, A to C is 1, but A to D is now 2. Right? Similarly, other distances are as shown in this particular matrix. So the distance matrix has changed. And what we do is we calculate the material handling effort, and the material handling effort is nothing but the flow matrix, which remains unchanged, which is what we have. Multiply it with this distance matrix, and again find out the total score. And for this particular case, the total score works out to 220. Right? This could be repeated for the second alternative. Second alternative, this is the layout. This is the new distance matrix. The flow matrix remaining the same. The total cost will be 265 by this procedure. For alternative 3, this is the new layout. This is the new distance matrix here. Again, the material handling effort with the flow and the distance will come out to 215, which you can calculate by the same procedure. Alternative 4, you will have again, this is the new layout A, D, C, B in this fashion, and again the material handling effort would be the flow matrix multiplied with this distance matrix, and this value is now 215. For the fifth alternative, the layout is A, B, C, D this way. The distance matrix is something like this. The total material handling effort is now 265 again. And we look at the sixth alternative, which is A, C, B, D like this. This is the distance matrix. So the material handling effort is flow into distance matrix, which is 220. It's quite a repetitive calculation, and therefore is best relegated to a computer. So once we perform all these computations, what have we got? We started with a layout, initial layout, which had a material handling effort of 265, and we have calculated the material handling effort for all these 6 layouts. What you then do in Craft is you select the one which is the lowest. So in this case, these 2 layouts give you the lowest possible score of 215. So what happens is that you can, this or this is a better layout than this one, and we can now use any of these layouts as the new layout and continue to repeat the procedure. So what we have illustrated to you is one basic iteration of Craft. That is how to go from one layout which had the initial layout which had a material handling score of 265 to a layout which has a score of 215. If it so happens that all these scores are higher than this score, that would show that this is the best layout available, so you stop there. So this is the stopping criterion in Craft. So we can this way determine the whole thing. After having seen the example of computation of a better or an improved layout, let's try to look at some of the limitations of Craft. What you find is that Craft yields a good heuristic solution that does not guarantee optimality. So the point that you must bear in mind is that you're not getting the best solution, you're not getting the optimal solution, but you're getting a good heuristic solution. Why is this? This is because not all the, if there are n departments, there are n factorial ways in which you can generate new departments. So instead of generating n factorial combinations, we are actually using at each iteration only NC2 pairwise exchange options are considered. And that means since we don't consider 3-way exchanges, 4-way exchanges and so on, we are actually confining ourselves to only these. So we are reducing the computational effort considerably, but we are being deprived of optimality in the process. In case departments are of unequal size, their centroids are exchanged, which can result in irregular shapes of departments. This is also a limitation in craft. This particular comparison between NC2 and n factorial will give you an idea of how much we are gaining in terms of computational effort. You can see that as n increases, the n factorial value is something like this, and the NC2 value is only this particular value. So really speaking, the problem of solving the problem for all n factorial values would be an exponential growth, and therefore it would be lead to so many possibilities, whereas in craft you are dealing with at a time only a very limited number of options. Of course, as n increases, for instance, if n is 20 or 30 or 40, the value for n factorial would be very large, and if you try to take it on your computer, on your calculators or computers, you will find that it won't be possible to accommodate that particular value, whereas 40C2 for instance is only 780 for this possibility. So much of the computational efficiency of craft comes from this factor, that you are evaluating only NC2 possibilities out of n factorial and therefore doing the solution. Look at the summary of the craft procedure. In the craft procedure, this example demonstrates one iteration of the basic craft procedure. The best layout so produced is compared with the starting layout. If it is inferior to the starting layout is declared optimal and the search stops. So this is the basic logic. Otherwise, a new iteration with the discovered layout as the starting node is initiated. So this cycle goes on as far as the start procedure is concerned. In conclusion, what we would say is that as far as computerized packages for layout planning are concerned, we have seen that they could broadly be classified into construction programs and improvement programs. And in this lecture, we had a glimpse of LDEP and CoreLab, which are essentially construction programs. That is, they derive a layout from a scratch. You don't have to supply the initial layout, they generate the layout either through random procedures or by references to the REL chart, as the case may be. And then we took an example of an improvement program in the form of craft, which was basically designed to take an initial layout and try to improve it through the process of pairwise exchanges. Most of these computations or improvements are based on the systematic layout planning procedure of Muther, which we studied in the last lecture. And there were two measures which were commonly specified. One was the activity relationships in the form of AEIOUX, and the other was the material handling effort. So for instance, in craft, material handling effort was taken as the objective function. In LDEP and CoreLab, the activity relationships determined the objective function. All these procedures are generally good for generation of alternative layouts, but they all have limitations, and the limitations are in terms of irregular shapes or ignoring any realistic real life constraints. That is why, although layout packages have been developed, they are never used exclusively for designing a layout. They are at best used for generating options which the layout planner examines, and then he may pick up one and modify the results that are obtained from the package by using whatever realistic constraints are there. So with this we conclude this particular session. Thank you very much.